3F, forces on an incline. Here's a quick overview of normal forces. An object at rest on a table is subject to an upwards force due to the table. This is the equal and opposite reaction of the table itself. This force is called the normal force because it's always directed normal or perpendicular to the surface of contact. The concept this is kind of referring to is that for every action, there's an equal and opposite reaction, and that every surface, such as a tabletop, is made up of tiny interconnected atoms. And as you place something on the tabletop, or as you push down on the tabletop, what you're doing is you're deforming or bending the relationship between these atoms. And what these atoms are doing is they're pushing backwards with equal and opposite force, kind of like a trampoline. So what you can kind of imagine is that the harder an object pushes down on the surface, the more these atoms and the springs connecting the atoms, kind of like a trampoline, the more they're going to push back. So the normal force is going to adjust itself so that the object stays on the surface without penetrating the object. So the normal force is adjusting itself to match the force that you're applying. And that makes sense because it's an equal and opposite force. So the harder you push, the more the normal force is going to push back. Let's think about it this way. Let's say you have a 1.2 kilogram book lying on a table. Since it's on the table, there's going to be a force normal pushing back. But if you were to go and push downwards with an additional force of 15 newtons, the force normal has to adjust. Otherwise, this book would start sinking through the table because net force would be downwards. In order for this object to be at rest on the table, the force normal has to adjust, and the force normal would become 26.76. So in this situation, the force normal is not equal to the force gravity. The force normal has adjusted to be equal to the sum of the downwards forces. Technically, the force normal will continue to adjust to the force that you're applying to it until whatever force you're applying overcomes the internal tension of the object. That's a concept for future physics, but every object has its own breaking point and the amount of force that it's able to withstand before it shatters. So until you reach that point, the more force you apply on an object, the more the force normal will increase. So if you push down with an extra 5 newtons of force, your force normal would increase to match that. So the next question is, what does force normal look like on an incline? It might be tempting to draw your force gravity downwards and your force normal upwards like this. But this is incorrect for 2 reasons. Number 1, remember that the definition of the word normal means that it's perpendicular. And this arrow right here is not perpendicular. It also doesn't account for the fact that an object on an incline can be sliding down the incline. So we have to draw this in such a way that force normal is perpendicular and that an object can slide down the incline. So your force normal is actually going to be drawn perpendicular to the surface like this. I didn't do that very well. Just a minute, let me fix that. That's a little better. All right, so this helps us answer the question, why does a object slide down an incline? And that's because we can kind of imagine our force normal acting upwards as being equal and opposite to this part of the force gravity downwards. And that the force that causes an object to slide down a ramp has to be parallel to the ramp. And that happens to be this part of the force gravity right here. So if there were friction, friction would be pulling like this. And if it was at rest, these two would be equal and opposite. But if it is not at rest, then our downwards force might be larger than our upwards force of friction, or there might be no friction at all. So it's this downwards component of the force gravity that is allowing an object to slide down the ramp. Here's a summary about forces on an incline. Remember that the normal force is always going to be perpendicular to the surface. So here's our normal force. That the force of gravity, or weight force, is always going to point straight down. We haven't talked about this yet, but when we rotate the x-axis to match the surface, the angle between the weight and the y-axis is going to be the same as the angle of the slope. We will talk about that in just a moment during our next example, because that text might hurt your brain. We also know that force gravity, or weight, can be decomposed into our x and y components. So what does that mean exactly? That means that our force gravity acting downwards is exactly the same as drawing the components of the force gravity down and over, and that these two x and y components of the triangle equal the hypotenuse of the triangle right here. So when we're solving, what we're essentially doing is we are kind of replacing this force gravity hypotenuse with its two x and y components. And that's why we're able to say that this equals this, and if the object at rest, that this would equal this. Two common mistakes to avoid. It is a very common mistake that you might draw your force normal straight up. That's incorrect, because the normal force is always perpendicular to the surface. That's part of the name. Normal means perpendicular. You might also be tempted to draw your weight downwards at an angle, and that is incorrect, because weight is always straight down, and that makes sense because gravity pulls straight down. Gravity doesn't pull at an angle. Gravity pulls straight down, so our weight would be acting straight down. Let's do an example using these principles. It says here that a car has a weight of 12,000 newtons. That means that our force gravity right here is 12,000 newtons. We could find its mass by saying its force gravity is mass times acceleration of gravity. 12,000 equals mass times 9.8. And that would give us a mass of 1224.5. We'll need that mass for later, but since it's giving us the weight, it's telling us the value of this force gravity right here. It says that it's parked on a 36-degree frictionless slope. So there's no friction. This force friction acting backwards is 0. There's no backwards force of friction. It says the brakes in the car fail and the car starts to roll down the hill. It wants us to calculate the force tending to cause the car to roll downhill, which would be this force compared to this force. And then it wants us to find the force the car exerts perpendicular to the hill, which would be this force, which we compare to this force. And then after that, it wants us to find the acceleration of the car and the velocity of the car after 30 meters. Let's start by calculating the force tending to cause the car to roll down the hill. The first thing we have to do, we know that this force gravity is 12,000. So this hypotenuse right here is 12,000. But what is this angle? Stop and think about it. There's a geometry principle that helps us determine what that angle is. If you think about it, this angle right here is 90 degrees. So what does that make this angle? So what does that make this angle? Surprise, the angle of incline of the hill is equal to the angle of this triangle right here. Let's use our sine, cosine, and tangent to find the yellow component of this triangle. I got 7053. Cool. Let's use now our cosine to find the green part of this triangle. I got 9708. That means my force normal is also 9708. So yeah, it says, what is the force tending to cause the car to roll down the hill? That's 7053. The force the car exerts perpendicular to the hill, that's 9,708. What is the acceleration of the car? That's an interesting question. I'm going to answer that over here. We know the mass of the car. We calculated that earlier, 1224.5. We're looking for the acceleration. What is the net force? If you look, you can see that this green line and this green line are equal and opposite. So the net force causing it to roll down the hill would be this yellow line downwards minus the yellow line of friction. And there's no friction, which means that the net force would have to be 7,053 down the hill. Using F equals ma, we can find the acceleration of the car, which is 5.76 meters per second squared. So next it says, after it's moved 30 meters, what's its velocity? This looks like a kinematics problem to me. We know it's starting at rest at the top of the hill. We know it's traveling 30 meters. We know it's accelerating at 5.76 down the hill. What would it be its velocity at the end? We can fill that in by saying v squared equals v naught squared plus 2a delta x. I did a calculation and I got an answer of 18.6 meters per second. So that's going to be its velocity at the bottom of the hill. Great job, guys. Let's try another example. Pro tip. If the object were at rest, the frictional force right here would be equal to the force causing the car to roll down the hill right here. But since there is no friction in that last problem, they were not equal. Our next two problems are going to have friction. Here's a diagram of a textbook resting on an inclined plane. We're going to find the following acting on the textbook: the net force and the coefficient of friction. Since this object is not levitating or sinking to the table, we know that the force normal upwards is going to be equal to this side of the triangle downwards. And due to our geometry principles, we know that this angle of incline is equal to this angle right here. Since we know that these two are equal and opposite, in order to find the net force, we're going to have to compare this downwards force to this backwards force of friction. I'm going to calculate the value of the bottom part of the gravity triangle. I got 12.61. That means that when we find our net force and we compare this downwards pull to this backwards pull, our net force is going to be 1.61 newtons down the incline. Next, let's find our coefficient of friction. We know that force friction equals mu times force normal. That allows us to calculate a mu of 0.61. There's no units on mu because it is a Newton divided by a Newton, so the units cancel. Let's do one more example. A skier goes down a 35-degree slope. Her mass is 70. Here's her force normal acting perpendicular to the surface. And it says the coefficient of friction between her and the snow is 0.15. That means that there is a backwards force of friction. We know that this here is going to be equal and opposite to our force normal. It wants us to calculate the acceleration of the skier and the skier's speed at the bottom of the slope. So to find the acceleration of the skier, we need to know her mass and her net force. The mass is easy, that's 70. To find the net force, we're going to have to compare the downwards part of this triangle to her backwards force of friction. So that means that we are going to need to fill in some values. All right, so I have this downwards force, 393, this sideways force, 561.9. That means our force normal upwards is going to be 561.9 as well. Let's find our force friction. 84.3. So in finding our net force, once again, the upwards force normal cancels the downwards part of that force gravity. So really we're comparing this, which is 343, minus our force friction, which is 84.3. I got a net force of 259.2, which makes our acceleration 3.7 down the hill. Knowing that if the slope is 40 meters and her acceleration is 3.70 down the hill, and she starts at rest at the top of the hill, what is her velocity at the bottom of the slope? I got a velocity of 17.2. There we go. Answered both questions. Nice work, guys.